I hope you can see my screen.
Yes, ma'am.
Okay. So, good afternoon, all. Today I'm going to take up the week 3 session and on the Introductory Organic Chemistry second NPTEL course. So, the course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputre from ISER Pune, and I'm your PMRF teaching assistant Simran. So, today we are discussing about the carbonyl compounds. So, this is the week 3 assignment. So I hope you guys went through my video of week 2 and you got all the answers. And if you have any doubt regarding that, please tell me.
No, ma'am, no doubt.
Okay, okay. So I'm continuing with this session, okay? So the problem one of this session is which of the following statements are correct in the case of carbonyl bond between carbon and oxygen? So the first option is the carbon is nucleophilic center, oxygen is the electrophilic center. The B option is oxygen is the nucleophilic center and the carbon is the electrophilic center. The option C is both B and D are correct, and the D option is carbon oxygen double bond is polarized. So before going to this question, first of all you guys need to know what is the structure of carbonyl bond. All right. So basically, this is the structure of carbonyl bond, and here, due to the electronegativity difference between this carbon and this oxygen, the electronegativity difference of these carbon and oxygen is high. That is why the dipole moment, which we have talked previously in the previous lectures, the dipole moment is more towards the more electronegative atom, that is the oxygen. So the dipole moment direction will be on the direction of oxygen upwards. So there is a polarization which develops between the carbon and oxygen bond due to the electronegativity difference. So a partial positive and a partial negative charge is getting developed. So a partial positive charge is getting developed on the carbon and the partial negative charge is developed on oxygen due to the electronegativity. As you guys know that the electronegativity of oxygen is higher than carbon. That is why it pulls the electron towards itself, and that is why a partial negative charge is getting created over here. Right? So here a polarization kind of thing is getting formed like this. A polarization is getting formed. A negative charge is getting arised on oxygen atom, while on the carbon atom there is a positive charge. So now coming back to the question, here they are asking the nature of carbon and oxygen. So first of all, we considers the nucleophilicity and the electrophilicity of the carbon and oxygen. So in the carbonyl bond, by looking at this structure, can you guys say that here a partial positive charge is getting created on the carbon? So now, will it be acting as a nucleophile to another species? No, right? Because it is highly electron deficient now. So it is not acting as a nucleophile here. Whether the oxygen atom is having a partial negative charge here, so it is acting as a nucleophilic species. Right. So the carbon in the carbonyl and oxygen bond is electrophilic in nature, while the oxygen here is nucleophilic in nature because after polarization, that is due to the electronegativity difference between these two elements, the carbon and oxygen bond is getting polarized. So after polarization, a partial negative charge is getting created on the oxygen, while a partial positive charge is getting on the carbon. So a negative anion is at oxygen and a positive charge is at carbon. So now we cannot say that the carbon is nucleophilic in nature because it lacks electron density. So it is electrophilic in nature. So the nucleophile, that is external nucleophile, can attack on this carbon. So we can say that it is electrophilic. While the oxygen here has a negative charge, so we can say that the electron density is high here. So that is why it is a nucleophilic center. Have you got this thing? Any problem in this? to here?
No, ma'am. No, ma'am.
Okay. So now coming back to the question. So they are asking in the question that carbon is the nucleophilic center and oxygen is the electrophilic center. Is it right? No, because here we can see, right, the carbon is a electrophilic center and oxygen is a nucleophilic center. Now in the option B they are saying that carbon is the nucleophilic center. So now this option is getting eliminated because we have seen that carbon is not a nucleophilic center because of the electronegativity of oxygen is higher than carbon, so that the carbon oxygen bond, that is a carbonyl bond, is getting polarized over there, and carbon is developing a positive charge, whether the oxygen is getting a negative charge because of the electronegativity difference. So now option A is getting eliminated. Now the option B is oxygen is the nucleophilic center and the carbon is the electrophilic center, which is right, right? We have seen that oxygen, due to the electronegativity, it pulls the electron towards itself and it acts as a nucleophilic center, while the carbon in the carbonyl bond is electrophilic and it external nucleophile can attack on the carbon. Now option C is both B and D are correct. So we have to look at D option. So carbon and oxygen double bond is polarized. So I have told you that due to the electronegative difference, the dipole moment is in direction of oxygen, and due to the difference between electronegativity, the bond is getting polarized. So we can write it as a partial positive and a partial negative charge. So this option is also correct, the option D, that the carbon and oxygen double bond is polarized. So this option is also correct. So now the correct option will be here. C option is that both B and D are correct. So B option is correct, we have seen, and D option is also correct. So correct option will be C, right? Have you got my thing?
Yes, ma'am.
Okay. So I'm proceeding to problem 2. I hope this answer is clear to all of you. So now the problem 2 is, what is formed when propanol is refluxed with an anhydrous solution of sodium borohydride? So do you know what is a sodium borohydride?
Reduction agent, ma'am.
Yes, it is a reducing agent. Okay, so if it is reducing agent, so the propanol structure is this, right? So if it reduces the carbonyl bond, what it tells you, that what is going to form? Any idea?
The oxygen is converted to hydrogen, ma'am.
The oxygen is converted to hydrogen. Actually, this ketone is getting converted into an alcohol. Not the oxygen is getting converted to hydrogen, but the whole group is converting into hydroxyl group. All right, because of the reducing agent sodium borohydride. So the options are propanol, propane 1-ol, propane 2-ol, propane. So for answering this, you have to know the IUPAC nomenclature, right? So which we have studied in previously. So guys, first of all, look at this. This is a reducing agent. Now, how it will reduce a ketone? So the mechanism of the reduction is, first of all, this the boron the BH4 minus, that is one of the hydride, will attack on the carbon of this carbonyl bond. As we have discussed that this carbon is the electrophilic in nature. Okay, so external nucleophile can attack on this particular carbon. So here the hydride, mark my words, the hydride, that is H minus, from this tetrahedral borane attacks on the carbonyl carbon, and the in turn it will attack on this boron, as boron is electrophilic here. So a tetrahedral species is getting developed here. Here the H is going to attach with this carbon and oxygen is attacking on this particular boron. So BH3 is getting connected towards here. After hydrolysis, now it will take up hydrogen from here, and this boron species is getting eliminated. So a BH3, the byproducts are the BH3, that is boron is getting formed, and NaOH is getting formed because the counter anion for this tetrahedral borane structure, that is a sodium borohydride. So the counter anion is sodium. So now it will react with this OH to form sodium hydroxide. So the byproducts are getting formed here, the BH3, that is borane, and sodium borohydride. So after taking up the hydrogen, this oxygen converted into the hydroxyl group. So here this ketone bond is getting converted into alcohol bond, right? So this is the mechanism how a reducing agent like sodium borohydride is converting the ketone into particular alcohol. So coming back, this mechanism is clear to all of you, or I have to
Yes, ma'am.
repeat? Okay, okay. So coming back to the question, now they are asking that if sodium borohydride reduces the propanol, which of the following species is getting formed? So if it is getting reduced, then a alcohol species is getting formed, that is a carbon with an OH. And here two methyls are there, right? And two methyls are there. I'm just writing it as R. So two methyls are here. So this species is getting formed when this propanol is getting reduced, right? So we have to answer according to IUPAC. So first of all,
Mm.
which species is getting formed? This is one, this is two, this is third carbon, right? So 1, 2, 3, that is propane, and at the position 2 we have hydroxyl group, okay, alcohol group. So we can say that this is a propane to all, because the OH group is attaching at the position 2, right? So propanol is the aldehyde. I hope you guys remember the IUPAC nomenclature, right? So for the propanol, it is used for aldehyde species. So the second option is the propane one all. That is one of at carbon 1 we have the hydroxyl species, but it is not the case, because after reducing propanol we have propanol at 2 position we having the hydroxyl group, okay. So option A and option B are not the answers. So option D, propane is getting formed. So propane, as you know, is a linear chain compound. So it is also not getting formed here. So the answer is propane to all. Because due to IUPAC nomenclature, we can say that this is 3 carbon species, and at 2 carbon we have an hydroxyl group. So it is propane to all. Right? Any confusions?
No, ma'am.
Okay. So I'm going to problem 3. So the question is, which is the main product of the following reaction? So this is the reaction, and we have to tell that which is the product which is getting formed out of these two steps. The first step is they are treating this particular compound with sodium ethoxide, that is a base, right? And in the presence of ethanol, ethanol here is just acting as a protic solvent, that is a proton source, right? So first of all, we have to look the condition 1. So after treating with condition 1, which is the species which is getting formed, we have to figure it out, right? So as you know, this is a strong base. Sodium ethoxide is a strong base. So what a strong base do? It will abstract a acidic hydrogen from the species, right? This is the system where we have this malonate and this 1,2 carbonyl, right? 1,2 alpha beta unsaturated carbonyl we have, and we have a malonate system. So guys, just tell me which is the most acidic hydrogen in these two species, which our base is taking up. Can you tell me? Just a guess. Do you understand what is a acidic hydrogen? Okay, I will tell you. See, what happens here, see, acidic hydrogen is that hydrogen uh, which is attached to a carbon which is electron deficient, right? It is not electron rich. So when you take up this carbon, this when you take up this carbon here, and conjugation is there, right? Two electron withdrawing groups are connected to this particular carbon. The electron withdrawing groups are these key ester groups, right? So these carbonyl groups are connected, and in between these this CH2 is there. So two electron withdrawing groups are there in which this CH2 is sandwiched, right? So they are withdrawing the electron density from this CH2. So this carbon is getting much more electron deficient, right? And now it has two hydrogens, right? It has two hydrogens. So if it has two hydrogens, and although this carbon species is very much electron deficient in nature now because of the presence of these two electron withdrawing groups. So this kind of arrangement in which the carbon is very much electron deficient, these hydrogens in turn is getting acidic. Acidic means they are getting in turn more electron deficient. So now it is very easy for a base to take up these hydrogens, these protons. So now I understand now the acidic hydrogen meaning. Is it clear or not? Then I will tell you again if it is not clear.
Clear, ma'am.
Clear?
Yeah, ma'am.
Okay. Just wait a minute. Okay. So now this base, that is sodium ethoxide, will take up a acidic hydrogen from the species, right? So I have told you that this is the acidic hydrogen here, this CH2, because here two electron withdrawing groups are attached to this carbon, and that is why it is making it more electron deficient in nature. And these hydrogen which is getting attached to this carbon in turn is getting much more electron deficient. That is why it is very easy for this base to take up these hydrogens. So a negative charge is getting created after this base is taking up this proton. So I will make it easy for you guys to understand. See what happens here. First of all, a carbon ion is getting generated at this position, right? And this carbon ion is conjugated with this particular carbonyl bond, and also with this bond on the right hand side, right? It is in conjugation with both of these carbonyls. Now it will attack the another species in the system is alpha beta unsaturated ester. Now this carbon ion attack on the 1,4 in 1,4 addition, and as in the conjugate addition it will attack on this carbon, and now this negative charge is now conjugated with this ketone. So the species which is getting formed here is now a O minus is getting generated when this conjugation is going to happen, right? So we have seen here the ethanol is also there in the system. So guys, just bother about only the first step. I'm explaining the step one only, and after that we will discuss in what the second step is going to do. All right. So just focus on the step one. In this step one, we have a base and a ethanol, that is a proton source. So when this anion is generated on this oxygen, this anion will abstract a proton from ethanol, right? Is it clear?
Yes, ma'am.
Yeah. So it will abstract a proton from oxygen, and after that, this species is getting formed. After that, this species is getting formed. See, after returning to the conjugation, a negative charge is getting created over there, right? And this negative charge is neutralized by ethanol, which we have in our system as a protic solvent. Sorry. This is ethanol, right? So it is getting neutralized by this ethanol by taking up this hydrogen. So this carbon ion will take up this hydrogen and getting neutralized, and we end up with this species. After step 1, we are ending up at this species. So I am repeating. See what happens in step 1. First of all, this base will abstract a acidic hydrogen. The acidic hydrogen is which, at this carbon, two electron withdrawing groups are there. This carbon is sandwiched between these two electron withdrawing group, which withdraws the electron from this carbon and makes it very much electron deficient in nature. And the hydrogens which are connected to this carbon is in turn much more electron deficient. So now this base will abstract a proton from here, and a carbon ion is getting generated over here. So this carbon ion is in conjugation with these two carbonyl groups. So it is going to give you a 1,4 addition. So a 1,4 addition is getting happen in this alpha beta unsaturated ester, and after the conjugation, this O gets a minus charge, and after this O minus is getting into this carbonyl bond again, and after this a carbon ion is getting generated here because this double bond is getting neutralized, right? So this negative charge will then abstract a proton from the ethanol which is present in the system, and which act as a proton source here, right? So this carbon ion is getting neutralized by abstracting a proton from here. So this is the species which we get after first step. This is the species which we get after first step. So just look at the second step. This is HCl, water, and the presence of heat. So we are treating this particular species with acid, water, and heat. So as you know, in the presence of acid, what happens here is these ester bonds are getting hydrolyzed. So this ester bonds, this ester species is getting hydrolyzed. So here, instead of OET, OH minus will attack here. OH minus, that is the, it will attack here. From water we have this OH minus, and it will attack here, this OH minus. It will attack here, and this goes up. After returning this negative charge, this OET is getting knocked out. Is getting knocked out, and for all of these ester, this mechanism is operative. So after that, a carboxylic acid is getting formed at all of the three position, and that is why we are getting a hydrolyzed product. So in the presence of HCl and water, we are getting the hydrolyzed product. From these ester species we are getting al- uh, the acid species, right? Is it clear? The second step, you guys understood or not?
Understand, ma'am.
Okay, okay. So coming back to the question, now we have uh, four options. So the option A is, just see at the, look at this product which we have, and just compare it with this particular four things. So the B option is also not correct, right? So the option B is not correct. Option C is also not correct, because here they are not neutralizing this uh, double bond, and they are attacking this carbon ion just at this carbonyl at 1,2 addition. Like 1,2 addition it is adding, and after that OET is leaving in this particular scenario. And we have seen that this anion is conjugated in between this carbonyl. So a conjugated anion will always give a 1,4 addition rather than a 1,2 addition. So 1,4 addition is not going to happen in this case. That is why it is not the answer. And also here, hydrolysis is taking place first of all, and after that this species is getting attacked on this. So it is also not the correct option. So option A is the correct one. So just see the mechanism, just understand the mechanism, what is happening here. Is it fine? Shall I go to the problem 4? Hope you guys understood this.
Yeah, ma'am.
Okay. So, the problem 4. So, they are asking what type of reaction takes place upon treatment of a ketone with HCN to form a cyanohydrin. So first of all, you have to look at the addition. What happens when the HCN is treated with ketone to form a cyanohydrin? So the mechanism for this particular reaction is like this. First of all, it is for aldehyde. Just to assume that this H is R in our case. Here we are talking about the ketone. So when we treat a ketone with HCN, how a cyanohydrin is getting formed, first we have to understand that to answer this particular question. So when we have a ketone, the HCN, that here we can say that this H is plus and C is in minus. So anion, so the nucleophile here is Cn minus, that is the cyanide group. So first of all, what happens here? An external nucleophile, that is the cyanide, will attack this carbon of this carbonyl bond, which is electrophilic in nature. We have previously discussed that this carbon is electrophilic in nature and this oxygen is nucleophilic in nature in the carbonyl bond. So an external nucleophile can add up on this carbon because it is electron deficient, and after conjugation, this oxygen is developing a negative charge, right? So Cn is getting attached here. After that, from as we have the protic solvents in this system, this O minus attacks on this H plus in the system and it forms a cyanohydrin. All right. So here, first of all, just look at this mechanism and just tell me that it is clear or not. Because one of the external species is getting attacked on the carbon, and after that, just the oxyanion is taking up the proton from the system, and that is how a cyanohydrin is getting formed. Why cyanohydrin? Because we have a cyanide group, that is Cn, and a hydroxyl group. So we call it as a cyanohydrin. So this mechanism is clear, right?
Yes, ma'am.
Okay. So just come back to the question. So they are asking what type of reaction it is. So when we are treating a ketone with a HCN, so what kind of reaction is going to happen? We have to answer this. So first of all, they are saying that is it a nucleophilic addition? Is it a nucleophilic substitution? Is it a electrophilic addition? Is it a electrophilic substitution? So, first of all, one thing is very much clear that an external nucleophile is getting reacted over here, right? This is the nucleophile. So, it is not an electrophilic addition for sure, because from outside we are getting a nucleophile, not an electrophile, right? So a nucleophile is getting reacted on this carbon, which is electrophilic in nature. So first of all, this option C and D is getting eliminated. Why? Because they are saying that an electrophilic addition is taking place. For an electrophilic addition to take place, the electrophile has to add on this carbon, add on this carbon, right? So this carbon is very electrophilic in nature, right? So how an electrophile is getting attached on this particular carbon? Is it possible? No, it is not, because it is even electrophilic, and you are saying that an electrophilic addition is getting take place on this particular carbon species. It is not possible. And it is also not the electrophilic substitution, because the electrophile is not getting substituted any of the elements in the particular species. All the elements at the ends are here only. This R species will be here, this hydrogen is here, this O carbonyl, which is getting into the OH, is also here. So nothing is getting substituted by the external species, which is an electrophile or nucleophile, right? So in this case, electrophilic addition and electrophilic substitution cannot happen, because to happen an electrophilic system, it should be a nucleophile. This carbon should be a nucleophile if an electrophile has to add on this, right? So option C and option D are incorrect because electrophilic addition or substitution cannot take place as the at the carbonyl carbon because it is even electron deficient in nature. So anything which is already electron deficient cannot add up an electrophile over it. Right? Is it clear why C and D are getting eliminated?
Yes, ma'am.
Okay. Because in HCN, the cyanide is an anion. The cyanide anion is the nucleophile, not an electrophile, which is acting on the carbon, right? So we have to consider this reaction only because they are stating that in the reaction of ketone and HCN to form cyanohydrin, what kind of reaction it is. So it is not an electrophilic addition and it is not an electrophilic substitution. So what it is? So here they are asking, is it a nucleophilic addition or a nucleophilic substitution? So nucleophilic is right word which is we have to use here because it is a nucleophile. Cyanide is a nucleophile which is getting attached on this particular carbon. So it is getting attached. Okay. This carbon is take up this cyanide and an addition is getting formed at this carbon. How? The Cn minus is getting add up on this carbon. Is it right? Yes, it is adding up on this carbon. Is it replacing any substituents? For the substitution reaction, it has to replace some element in the system which is already present, right? Is it replacing any element? No, because all the species which is present in the starting material, you end up in the product. Both R and H, in our case it is R, right? Both R is there, both oxygen is there. Cyanide is just getting add up on this particular carbon. It is not displacing the substituent on this carbon. So any substituent is not getting displaced from this carbon. That is why we are saying that it is not a nucleophilic substitution. Because for substitution, as the term suggests, that for substitution, a nucleophile must substitute a element in the starting material, right? So in the starting material, this nucleophile is not substituting or taking place of any element because all the all the elements in the reactant is still there in the product. So it is a nucleophilic addition rather than a nucleophilic substitution because only Cn minus is getting add up on this carbon and nothing is substituted because of this Cn minus. Right? So the correct answer will be, just tell me the correct answer if you got this particular thing.
Option A, nucleophilic addition is the right answer, ma'am.
Very good. So it is a nucleophilic addition because substitution is not going to happen in this case. Why substitution is not going to happen? Is it clear? Because the nucleophilic substitution to happen, Cn minus, that is a nucleophile, it has to replace anything from the starting material. If it is not substituting or replacing any substituent, in this particular starting material, then it is not going to have a nucleophilic substitution. All right, it is only adding up on the carbon and nothing else it is doing here. All right, so we have the answer. Nucleophilic addition is going to take place when we treat a ketone with HCN to form a cyanohydrin, right? So I hope this answer will be clear to all of you. So I'm going to problem 5. So in the problem 5, they are asking the oxidation of primary alcohols give. So oxidation of primary alcohols. We have seen the reduction of ketones to form the alcohol in the previous case in this question number 2, right? So now they are asking what happens when an oxidation of primary alcohol is going to happen. So the structure of primary alcohol is this. In this primary alcohol, one of the R group is present on the carbon and all the two are hydrogens. In the secondary alcohol, two alkyl groups are there. In tertiary alcohol, three alkyl groups are there. So all the hydrogen are getting substituted by the alkyl groups. So now when we oxidize this particular primary alcohol, so after oxidation, what it will give you? An aldehyde, a ketone, or both A and B. aldehyde, ketone, both, or alcohols. See, after oxidation, it is not going to give you alcohol because already it is a alcohol, right? So oxidation will either give you an aldehyde or either give you a ketone, right? So D option is not correct because alcohol oxidizing to alcohol is not possible, right? So what happens here is, in the case of primary alcohol, we have two hydrogens here. So only one alkyl group is there. So after oxidizing, so OH will oxidize to give you a ketone moiety or an aldehyde moiety. So basically it will have a carbonyl. So it is going to give you a carbonyl after oxidation, right? So what happens here? The hydroxyl is giving you a ketone group. So assume that it is forming a ketone here. Sorry, a carbonyl bond here, right? CO, a carbonyl bond here. So now tell me that if it is forming a carbonyl bond here, so one of the H group is substituting here. So H group is going. So it just have an H and R group. So a species like this is getting formed. So we are getting a species like this. So it is a aldehyde or an ketone? Just tell me. It is
Aldehyde, ma'am.
an aldehyde, right? So primary alcohol, due to because it has only a single substitution of alkyl group, it will give you an aldehyde. If we talk about the secondary alcohol, right? So what happens here? So after oxidation, this OH will give you a carbonyl group and this H leaves. So this RR, both are alkyl group. So what will it will give you? The end product will be like this, right? The end product will be like this for secondary alcohol, I'm saying. So what is it?
Ketone group.
Yeah. So, do you understand now? This primary alcohol after oxidation will be giving you a aldehyde, whether a secondary alcohol will give you a ketone because of the presence of two alkyl groups, right? So they are asking in the question. So after oxidation of the primary alcohol, what we are getting? Aldehyde, ketone, or both? So what is the answer according to you? See, they are saying about the primary alcohol only. They are not asking about a secondary alcohol. So we have to be very rigid. If they say that the after oxidation of alcohols, what will you get? If they say that only alcohols oxidation are they asking, so we can say that yes, the aldehyde and ketone both are getting formed, both are the possibilities which will be formed, right? But they just rigid the question to primary alcohol, they restrict the question to primary alcohol. So after oxidation, what they are giving, we have discussed here that these species are giving an aldehyde only. They are not going to give you a ketone because they do not have another alkyl group, right? They have only one single alkyl group and both of the substitution are hydrogens. So you are ended up with an aldehyde only, right? Got it or
Yes,
not?
ma'am.
So the answer will be A, not the B, because on the oxidation of secondary alcohol you are going to get a ketone. Not option C, because if they are asking that the oxidation of alcohols give what, then you can say that yes, both aldehyde and ketone can be formed because in the alcohols we have three categories: a primary, secondary, tertiary, right? And if you call about the tertiary oxidation, so the tertiary alcohol doesn't go for the oxidation because they doesn't have an hydrogen to leave, right? So they are not going to give you a oxidized product. Okay, is it clear?
Yes, ma'am.
All right. So I'm going to problem 6. So just look at this problem. It is a bit difficult, but you will understand if you go through the my words, right? So they are asking, this is a bicyclic system, right? This is a bicyclic system and have a lactone species. So after treating with ethoxide in the presence of ethanol, we have seen that sodium methoxide or potassium methoxide in presence of ethanol, they are acting as a strong base, right? And ethanol here is the proton source only. So now they are saying that which of the following product is getting formed, and we have to specify the stereochemistry as well. So if you cannot see this, this is a dash bond, right? This is a dash bond. Here also it is a dash bond. So we have to justify the stereochemistry as well after answering this question. So this is the bicyclic system, and now we know that an ethoxide, what it will do, it will either abstract a acidic hydrogen or it will act as a nucleophile. If the system doesn't contain a acidic hydrogen, then this base will act as a nucleophile, right? So we have a carbonyl in this system. Is it have does it have any acidic hydrogen? See, the hydrogen which is present in this system is two hydrogen here, two hydrogen here, two hydrogens here, one hydrogen here. This is hydrogen, right? So if this oxygen is replaced by the CH2 group, then you have a acidic hydrogen, because this electron withdrawing group is just withdrawing the electron towards this CH2, right? So instead of oxygen, if you have a CH2, then the system has an acidic hydrogen. But now in this bicyclic system, it doesn't have an acid that much acidic hydrogen in the system. So now the ethoxide is acting as a base, sorry, as a nucleophile rather than a base, because the system doesn't have an acidic hydrogen. Is it clear that what is an acidic hydrogen? I will recall it, that if the carbon is very much electron deficient in nature because of the presence of electron withdrawing group here, then the hydrogen which are connected to this particular carbon is rather more electron deficient. So these hydrogens are now become acidic, that is the electron deficient. Now the base can take up this hydrogen to form a carbanion there. But in this case, there is no acidic hydrogen, so now this base have no option to act, rather to act as a nucleophile only, right? So now this carbonyl group is present in the system, so it will be acting as a nucleophile. So we have two possibility. Either this ethoxide will attack on the from the above side or from the below side of this ketone. So this ketone is planar, as we know. This sp2 hybridized system is planar. Now this planar system has two possibility, that either the nucleophile come from the above side or from the below side, right? Two possibilities are there. So as we know, this is a bicyclic system, so it is a half this is a open book like system. So if you call upon a open book like system, so now this open book like system has the above side is much more free, because the downside, it is a cavity. See this downside, if you imagine in 3D, this downside has a cavity. So this cavity, due to this cavity, it is very much hindered here. So nucleophile cannot add up from the below side because of the cavity. Now this cavity will hinder the attack of the nucleophile from the below side. So nucleophiles have only one option, to come from above side. See here, there are hydrogens which do not do the steric hindrance in that much case, right? So here they have a cavity due to the open book like structure of this bicyclic system. The cavity is there below, so the nucleophile is feels very much hindrance in coming from the new below side. So attack of the below side of this nucleophile is not possible, so it is end up with only above side attack, right? For the stereochemistry, it is very important to see that whether the nucleophile is adding up from the above side or the below side. That is why I'm explaining this concept. If it is a if the stereochemistry we don't have to mention, so we doesn't bother about how this ethoxide is coming from above side or the below side. But for the stereochemistry sake, you have to know whether this nucleophile is adding up on the above side or the below side, right? So due to the bicyclic system, a cavity is here. When you imagine in 3D, it is an open book like system, and if the cavity is here, the cavity is down side, then the nucleophile is not approaching from the downwards. It is approaching from the upside of the system. Is it clear? The nucleophilic attack is clear or not? Just tell me that.
Ma'am, I had a doubt, ma'am.
Yeah, just ask me.
Um, if the system, I mean, the substrate as not having a acidic proton,
Yeah.
then the strong base like sodium ethoxide act as a base. Am I right, ma'am?
See, what happens that if the system doesn't have an acidic hydrogen, right? So the sodium ethoxide base, that is a strong base, will act as a nucleophile, not the base. Because for acting a base, it should abstract a proton, right? What is a characteristic of a base? The characteristic of a base is that a base abstract a hydrogen, right? A proton from the system. But a nucleophile attacks on the system, right? So if you doesn't have a acidic hydrogen in the system, then a base, a strong base like ethoxide, will act as a nucleophile rather than a base because it doesn't have a acidic hydrogen. Is it clear? Now, in this case, it is acting as a nucleophile rather than a base.
Okay, ma'am.
Yeah, that is why it is attacking on the carbonyl as a nucleophile, not like a base. Okay.
Okay, ma'am.
Yeah. So the attack is clear that ethoxide, why is it attacking on the above side only? Why it is not attacking on the below side of this carbonyl? Is it clear?
Yes, ma'am. Because of the gravity, it doesn't react at the back below side, ma'am.
Yeah, very good. So because of the cavity, if you imagine it in a 3D structure, right? So this bicyclic system is very much strained from the downside. That is why this particular nucleophile is attaching on the above side only, right? So we get this compound after the attachment of this ethoxide to this carbon. So carbonyl group now develops a negative charge here, right? When conjugation is going on. But we have to remember that in the system we have ethanol. We have ethanol. So ethanol, what it will do? It will give a proton to this oxygen ion, and now OH bond is getting formed, right? So I'm just clearly writing this as an OH. But first of all, this carbonyl is oxygen ion is getting formed because of the conjugation, and after that, this oxygen ion is abstracting the proton from here, right? And after that, this OH bond is getting, right? So I'm skipping one step. Just keep in mind that this protonation is going to happen first. After that, this hydrogen oxygen bond leaves to give you this thing that oxygen is again getting generated here. This bicyclic system is getting cleaved. Why this bicyclic system is cleaved? See what happens. OET has a tendency to leave. We know that OET is a good leaving group. Okay, but now this, after cleaving this OH bond, this is not leaving. This is not leaving. Why? Because the bicyclic system is strained system. This is a strained system. So it wants to just neutralize the strain. Just a minute. I think I missed there. All right. See, after cleaving this OH bond, now, ethoxide can be leave, but it is not happening in this particular scenario because the bicyclic system is very much strained, and now it wants to just release the strain. So that is why instead of this ethoxide, the carbon oxygen bond is getting cleaved here, right, to neutralize the strain. Okay. So if it cleaves here, this oxygen ion is getting formed again. Now, ethanol will again gives the proton to this particular oxygen ion, and this species is getting formed. So, a five-member species is getting formed. One cycle is getting released, right? One cycle is getting uh, cleaved, and that is why the cyclic bicyclic system, it is releasing the strain. So now the ring size is how we have to calculate it. This is one, this is two, this is three, this is four, and this is 5, right? So a 5-member system is there. So a 5-member species is there, and just we have to figure it out that what are the substituent which is attached at the particular thing. So if it is one, this is, sorry, This is 2. If it is 1, this is 2, this is 3, this is 4, and this is 5. So according to this, we just uh, appropriate substitutions are there. At 1 we have this carbonyl, this aster group. At 3 we have this hydroxyl group, right? We just wrote it in a planar fashion. So now, this system, how the stereochemistry is there, because this ethoxide is adding up from the above side only. That is why after cleave, OH bond cleave, this carbonyl bond is getting formed here, right? So this carbonyl bond is above the plane because the ethoxide is getting from the above, right? So this CO double bond O, that is a planar system. So now this whole thing is above the plane. So that is why after cleaving this particular thing, it is cleaving from the above only. See, this bicyclic system is in one above the plane, right? So below there is a cavity, and that is why ethoxide is adding up from the above side. And this OH bond, after cleaving, a carbonyl bond is getting generated, which is a sp2 hybridized species, and that is why if this ethoxide is in above the plane, that is this whole group is present in above the plane. So this above the plane species, after cleaving this CO bond, this OH is also present in the above the plane. So the plane of both the things, both the substituents are same. So these are connected as a cis fashion, right? Is it this stereochemistry thing is clear to all of you?
Yes, ma'am.
All right. So I will just for the sake, I will repeat it again. See what happens here. First of all, this ethoxide will come from above side because there is a cavity, and now this is the hindered region. That is why this nucleophile will attack up from the above side, and this carbonyl is now this delocalization is taking place, and after that this O minus will attach a proton from this ethanol, and this OH bond is getting formed. After that, this OH is getting cleaved and the carbonyl bond is getting formed here, which is sp2 hybridized, and the ring chain is getting released after the formation of this hydroxyl group. So this OET is present in the above the plane, so this whole group is lies above the plane, and now the cleavage of this CO bond, this hydroxyl is also coming above as this particular stereochemistry. So the stereochemistry of both these substituents are same. So we can say that a five-member species is getting formed at 1 and 3. We are having a cis configuration of both the substituents. So the end product is this. So coming back to the question, we have both 1 3 cis products in the system. So A is not the answer. 1 3 is the answer, right? 1 3 substituted five-member ring we have. So A is not the answer, C is also not the answer, D is also not the answer. Correct option is B. Right? Shall I go to the problem 7? Is the answer clear to all of you?
Yeah, ma'am.
Alright. So coming to the problem 7, they are asking the correct order of decreasing reactivity of the given compound towards hydrolysis under identical condition. So they are asking the rate of hydrolysis. So we have to arrange it in the correct order of decreasing reactivity towards hydrolysis. So for the correct order of hydrolysis, we first have to figure it out. This is the acid chloride, this is the amide, this is the acid anhydride, and this is the ester. So this is what they are asking, that the hydrolysis rate in these particular species, how it is arranging, right? So first of all, we have to look at the reactivity of these species toward hydrolysis, and then we arrange it in a decreasing or an increasing order, right? So just tell me, this is an acid chloride. So for hydrolysis, OH minus is the nucleophile which is attacking on the carbon of this carbonyl, right? You understand na? This hydrolysis is what? The attacking of the OH minus which is coming from water to the carbonyl carbon, right? So how much it is easier for this hydroxyl to attach on this carbonyl is depends on the electrophilicity of the carbon. If the carbon of the carbonyl bond is very much electrophilic in nature, right? So this attack of this nucleophile is much more facile, right? So we have to figure it out which is the more electrophilic carbon amongst these. So as we know that Cl is an electronegative atom, so it makes this carbon much more electrophilic in nature. So now the attack of this nucleophile this to this particular carbon is very much easy. So now this hydrolysis rate of this acid chloride is very high because of the electronegativity of this Cl. Right. Now coming to this acid anhydride, we are saying that yes, this is the electrophilic in nature, right? So now coming to this acid anhydride, we have to arrange it in the decreasing order. So we will arrange it in decreasing order. First, we have to see which is the more electrophilic carbon amongst these carbonyl bonds, right? So now coming to the acid anhydride, this oxygen has the lone pair of electron. So this oxygen lone pair is in conjugation with this particular carbonyl groups. So these two carbonyl groups are engaged in the conjugation with this oxygen. Is it right? Yes. So now, if it is engaged in the conjugation, now a double bond character is developing between this C and O bond, right? Because of the conjugation, this is going up, so an oxyanion is getting formed, but an partial double bond is getting formed between carbon and oxygen due to delocalization. So now it is not that much electrophilic in nature due to conjugation, because now this oxygen has the tendency to conjugate with both of these carbonyls. So now the electron density at this is like diverted to both the carbonyls. So now there is much less chance that both of the carbonyl is getting polarized simultaneously. All right. So here the conjugation is there. That is why this carbon is not that much electrophilic to attack by a nucleophile. So now coming to this ester. Now the oxygen is again in the conjugation. This lone pair is again in the conjugation with this system. Now the oxygen lone pair has a single carbonyl in which it has to uh, give its electron, right? So there is only one carbonyl at which this oxygen lone pair is donating the electron to form the conjugation, right? There is no another carbonyl, so it is focused on this particular carbonyl. So it increases this partial double bond character which will be coming on this carbon oxygen bond due to delocalization very much. So now the tendency of formation of the carbon oxygen double bond here is very high due to delocalization. So this carbon is in turn is very not that much electrophilic because a double bond character is arising at this particular species, right? So how it is getting electrophilic? No, it is not an electrophilic species. So here also, when we come to the amide, the electron donating power of nitrogen is very high than oxygen. We know this because of the electronegativity. We know, right, that electronegativity order of the halogens are like this. The first of all, fluorine is the most electronegative atom. After that, the oxygen, and after that, the nitrogen. So when we come to this, the nitrogen is much less electronegative in nature. So it has more electron donating power. So it the partial double bond character which is arising at this carbon and nitrogen is in turn very much high. So now the electro which just decreases the electrophilicity of this carbonyl carbon. So now this carbonyl carbon is very is the least electrophilic, is least electrophilic. Why? Because nitrogen lone pair is now in the particular conjugation with this particular carbonyl. So now the higher the conjugation with this carbon, greater is the double bond character which is arising between the carbon and nitrogen bond, and that is why the electrophilicity character of this carbon and nitrogen bond is very less. So an external anion cannot act on this very much facile because Now here it is not in that much electrophilic. So now how can a nucleophile can attack on a less electrophilic carbon? So the ease of hydrolysis in the case of amide is low. So similar to this, the electronegativity of this oxygen is higher. That is why the donating power of this oxygen towards this carbonyl is lower than nitrogen. Just mind that this conjugation is here is also there is a conjugation and a partial double bond character is developing between carbon and oxygen, but due to electronegativity the oxygen is not that much effective donor than the nitrogen. So that is why it is also electrophilic, but now here the least electrophilic carbon amongst these four species is with amide, because the ease of delocalization here is very high. So if the ease of delocalization is very high, so the carbon nitrogen double bond character is high. So if it is high, then we have a lower chance of nucleophilic attack. So hydrolysis rate is low for this, which is low for this as well, but higher than this, and which in turn is lower than this but higher than this. How it is higher than this ester in acid anhydride? Because now the lone pair of oxygen is donating to both of this carbonyl. So at a time it is donating to only a single carbonyl, right? So one of the carbonyl carbon is electrophilic in nature at a time. Here, both the electron density of this oxygen is donating to both the oxygen's carbonyls. So, at a time, it is donating to only one carbonyl, and another carbonyl is left with electrophilic nature. So, now that is why this anhydride has a higher ease of hydrolysis, because the carbon is higher in electrophilicity than this ester group, which in turn this acid anhydride has the highest ease of hydrolysis, because the electrophilicity at this carbon is much higher because of the electronegativity of this Cl. It will attract the shared pair of electron towards itself, and that is why making it much more electrophilic. So, if we have to arrange it in a decreasing order, so first of all, acid anhydride has the highest ease of hydrolysis because of the electrophilic nature of this carbon. And this acid anhydride is the second one. Then ester comes, and then the amide comes. So coming to the option A, B, C, D, which matches to this particular thing is in the option A they are saying this acid chloride is highest, then amide. No, amide cannot be greater than this anhydride, because amide has more tendency, nitrogen has more tendency to go in the delocalization than the oxygen. So it is making this carbon less electrophilic. That is why A is not the correct option. Now going to see, so first of all, they are saying that highest electrophilic character of this ester is there, which is not the case, because highest electrophilic character is with acid chloride only. So this is also not the answer. This is also not following the trend, because it is saying that acid anhydride is the highest ease of hydrolysis. The correct option is B. The acid chloride has the highest ease of hydrolysis than acid anhydride, which in turn has the highest electrophilic character than ester, which in turn has the highest electrophilicity character than amide. Is it clear or not? This answer. Any
Yes,
doubts?
ma'am. Clear, ma'am.
Okay. So I'm going to problem number 8. So nucleophilic substitution at acyl carbon of carboxylic acid derivative generally proceeds by. See what they are saying, that the nucleophilic substitution at acyl carbon of carboxylic acid derivative. So carboxylic acid derivative, we have to take a carboxylic acid derivative in account. A derivative is an ester. So acid carboxylic acid derivative here is we are taking as an ester. So they are saying that nucleophilic substitution at this acyl carbon, that is this carbonyl carbon, the nucleophilic substitution is generally preceded by. So they are simply asking about the nucleophilic substitution. So simply a nucleophile is, first of all, what happens here? It is adding up to this carbon, and after that this addition is taking place. After that an elimination is taking place, because they are saying that Here the nucleophilic substitution is taking place. So we have seen that the substitution is only taking place if the nucleophile is displacing or substituting any of the species in the starting material. So this is the starting, this is the reactant. Here in the product, we have this displaced methoxy group. So here, what happens when this oxy anion comes back? This methoxy knocked out. So after that, this aldehyde is getting formed. So it's ketone, whatever it is. So depending on the nucleophile. So the trend with the nucleophilic substitution is, first of all, an addition elimination mechanism, an elimination addition mechanism, SN1 mechanism, and SN2 mechanism. So which is the trend which is following while the nucleophilic substitution is taking place at the acyl carbon? So what happens? First of all, as you can see, nucleophile has to add on this particular carbon, and after that, and elimination is taking place. So the trend is, it is not following the SN1 mechanism, it is not following the SN2 mechanism, because in SN1 mechanism a tertiary carbocation is getting formed, a carbocation is getting formed basically. Here no carbocation is getting formed. In SN2 a carbon anion is getting formed, but here it is a oxyanion which is getting formed. So it is not an SN2 mechanism as well. So we have to debate in between these two options. Is it a addition elimination or a elimination addition mechanism? So depending on the nature of the steps, we have to decide. First of all, this nucleophile is adding on this particular carbon, and after that this oxyanion is coming back and elimination of this methoxy is taking place in nucleophilic substitution, right? So the addition order is like, first of all this addition of nucleophile is taking place, and after that elimination is taking place. So the mechanism which is operative here is A, not the B, because elimination and addition is not the mechanism, because first of all addition of nucleophile is very important to eliminate anything in the nucleophilic substitution, right? Is it clear?
Yes, ma'am.
Okay. So if it is clear, I'm going to the problem 9. So ketones are comparatively less reactive than aldehyde. It is due to, first option is alkyl group are electron donating, Bi is the steric hindrance, C is the both A and B, and D is none. Okay. So as you can see, ketones are comparatively less reactive than aldehydes. They are stating this particular statement and they are asking why is it so. So it is the ketone and it is the aldehyde species. This is ketone, this is aldehyde. So we have to figure it out that why the ketones are less reactive. Ketones are less reactive because in the ketones we have two alkyl groups, right? We have two alkyl groups. So both of the alkyl groups have plus I effect. We have talked in the previous lectures what is a plus I effect and how it is um, affecting on the NMR, right? So similar case here, these two alkyl groups have plus I effect. Plus I effect is, it intensify the electron density at this particular carbon due to the plus I effect. It has electron donating effect. So carbon is much more electron rich here, and that is why it is less reactive, because if the carbon of this carbonyl, we have studied that it is electrophilic in nature. So anything which is increasing the electron density towards this carbon, it is making less reactive towards the nucleophilic attack. Towards the nucleophilic attack. We have seen that the nucleophilic attack is facile if the electrophilicity of this carbon is high. But here, in the case of ketones, these two alkyl group increase the electron density at this carbon, and that is why they are making it less reactive towards the nucleophilic attack than the aldehyde. Because in aldehyde we have only one alkyl group, and there is no other alkyl group which imparts the electron density towards towards the carbon, and which makes the carbon less electrophilic. So, if I ask you which of the carbon is more electron rich here, so what you will say? Is it the ketone carbon or is it a aldehyde carbon which is more electron rich? So you can clearly see that in the case of ketone, the carbon is much more electron rich than aldehyde. So for the reactivity, we have to make it more electrophilic, right? So here in the ketones, it is less electrophilic than aldehyde. So the reactivity of these ketones is much less than aldehyde due to the presence of these two alkyl group, which is imparting the electron donating effect, right? So the coming back to the question, here they have asked that is it the alkyl group which are donating steric hindrance or both A and B? See, the nucleophile also feels some steric hindrance when it comes closer to it. If it is CH3, CH3, these are groups, then you can feel that after during attacking of this nucleophile towards this carbon, a steric hindrance is also there because methyl group in turn is more bulky than hydrogen. So that is why it is both the reasons that A and B both are the reasons due to which the ketones are less reactive than aldehyde. So option C is the correct one because alkyl group increase the electron density at this carbon and also due to the steric hindrance. When we compare it with the aldehyde, there is a R group here which increases the steric hindrance here after, in the attacking of this nucleophile. So it makes more uh, it makes it difficult for this nucleophile to attack this carbon due to steric hindrance as well as the donating effect. So C is the correct answer. So is it clear?
Yes, ma'am.
Okay. So now I'm coming to the last question of this session, the problem 10. So they are asking that among the following, the compounds having the highest enol content. Enol content, right? What is a enol? First, you have to know. These are the options. So I am just taking up this in this slide. So what is an enol content? So we have seen that this is a ketone. All right. So if this ketone has an acidic hydrogen here, so a base can abstract it and then corresponding anion can get formed. Right. This anion is getting formed. So this anion can delocalize with this particular ketone. And what forms here is known as enol. This is en and this is all. Right? So this is what we say an enol system. So they are asking which of the species has more enol character. So for this particular thing, this anion has to stabilize. Just mark my words, this anion, if it is formed after the abstraction of this acidic hydrogen by a base, it has to stabilize for the formation of this enol system. So if we come to this particular aldehyde, so after the formation of an anion, this CH2 minus, because one of the hydrogen is taken up by the base, then an anion is getting formed here. So this anion is delocalized with this system. And in this also, it is getting delocalized. So it is this also. So how much this anion is getting stabilized, that is how much the enol character is in the particular system. So if it is more stabilized, more is the enol character which is present in this particular system. So we have to see that how many carbonyls are there to stabilize this particular anion. If more is the conjugation, more is the carbonyl that is present for the stabilization of this particular carboxy anion, we can say that yes, the enol character is high. So in both the aldehyde and ketone, same kind of things are there, but aldehyde is much reactive, so we can say that yes, the enol character is high for this particular species than ketones. But we have to select one option amongst this. We have doesn't have to arrange in the particular order, so we have to select one of the correct answer. So now here, when the carboxy anion is getting formed, so first of all, just mark the acidic hydrogens which are there and how the carbanion is getting formed. In the presence of base, these are the locations at which the carboxy anion is getting formed in both the four of this, right? In all the four of this. So just go through this. This carboxy anion is stabilized by two carbonyl groups. by two carbonyl groups due to delocalization. In this case also they are stabilizing by the two carbonyl groups. But so aldehyde and ketone, amongst these four, these two are those these two are those which are more enol character than the carbonyl and aldehyde. Why? Because in the ketone and the aldehyde there are only one carbonyl which is here to stabilize this carboxy anion, and that is why the enol character is not so much high of these ketone and aldehyde than these two dicarbonyl species. So this 1,3-dicarbonyl species have more enol character. So now in among these two, we have to figure it out which of these have more enol character. So now the stabilization of this carboxy, and I will tell you that. See, in this case, the oxygen has a lone pair. So it has also tendency to resonate with this. So it is also in the resonance with this carbonyl group, which makes this anion resonance difficult to happen. So now this anion is resonating with this carbonyl very efficiently, but with this carbonyl ester carbonyl, it is difficult for this carboxy anion to resonate and to stabilize this, right? So that is why, and when you compare this with this aldehyde, here this carbonyl doesn't have any other conjugation than this particular carboxy anion. But that is why it is very much stabilized by these two carbonyls rather than this ester carbonyl, because oxygen lone pair is also in the presence in the conjugation with this carbonyl compound, and that is why it restricts this conjugation from the carboxy anion. So that it is not that much facile which is present in this case. So this particular compound is much more having much more enol character because of the higher stabilization of this carboxy anion than this. Are you getting my point? See how many carbonyls are there, it will decide at how much stabilization is there for the carboxy anion. So we have ruled out these two because it has only one carbonyl, but these two have two carbonyls. So uh, this carboxy anion is much more stabilized. So if it is stabilized, then a enol content is high. It has higher tendency to form the enol system. So in this, among these, we have seen that this oxygen lone pair is in resonance between this particular carbonyl, and that is why this carboxy cannot efficiently resonate with this carbonyl. Rather, it is resonating efficiently with both of this oxygen here, right? So, which of the among two have high enol character according to you? I'm asking about these two only, right? We have ruled out the ketone and aldehyde. But in these two, which has more enol character? Just a guess. Any idea?
The methoxy group is less compared with the
Methoxy group is, sorry. See, here this oxygen is present in the conjugation with this carbonyl, right? So that is why it is making difficult for this carboxy anion to resonate with this carbonyl. So there is a hindrance because of this ester oxygen. Okay. That is why this carboxy anion is not that much localized with this carbonyl. But in this case, it is very much efficiently localizing with these two carbonyls. So it is higher stabilization is there for this particular carboxy anion. So higher is the enol character. So the correct option is this. Okay, it has much more higher enol character than all of the four. So the correct option is C. It has more enol character. Is it clear? Clear? Okay. So it is, if it is clear, then I'm just stopping my session today. And I hope these 10 questions are clear to all of you. If it is not, then just let me know in the next lecture and I will solve the problem which you guys are having. Okay. So thank you so much, and thank you so much for listening me patiently. Thank you for attending my course, and we will be meeting on the next Sunday at 3 to 4. Right. So thank you so much.